Hello everyone. So today we're going to hopefully finish up 13.3. So hopefully this will be the last video in 13.3. So we actually come to the end of the section already. I just want to give you maybe another example, and that will probably be it. But before I do that, let's just quickly do a summary of what we have learned in chapter 13. So let's say we're given a linear system in what we call the standard form. So what do I mean by standard form? Meaning d vector x over dt equal to some matrix function a of t multiplied by vector x plus some vector b of t. We can find the solution by kind of following the following step. We can try to solve this system with the following steps. So the first one we're going to do is this. If vector b of t is not the zero vector, then that will imply that what we have is a non-homogeneous system. So if that's the case, then we're going to have to try to solve for two things: the homogeneous solution and the particular solution. So let's start with the first step. We can find the general solution to the associated homogeneous system. So what is the associated homogeneous system? Is d vector x over dt equal to a of t vector x. But how? By using a elimination method, b eigenvalues and eigenvectors, so when I say eigenvalue, eigenvector, remember that the solution vector x is always equal to c1 e to the lambda 1 vector u1 plus c2 e to the lambda 2 vector u2 plus dot 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 all the way to c sub n e to the lambda n. Oops, forgot the t. Ugh. You know what, I'm going to rewrite. Alright, c1 e to the lambda 1t vector u1 plus c2 e to the lambda 2t vector u2 plus dot 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 plus c sub 3 c sub n lambda sub n t vector u sub n. So that's how the solution always look like. Or as a matter of fact, we have a second formula for that. Or vector x equal to u lambda sub t c vector c. And yes, we could also do u lambda sub t u inverse x sub 0, but that's for a particular solution that's satisfied the initial condition. Okay, here we're just trying to do general solution to the associated homogeneous system, so we don't use that. Or we could also using part 3 matrix exponential, which is e to ta. In this case, our solution vector x is actually equal to e to the ta multiplied by some constant vector c. So any of these three methods are available to you depending on which one is easier to do. I would say eigenvalue, eigenvector pretty straightforward as long as they don't have any repeated eigenvalue. And finding eigenvalue, eigenvector is not as bad. Elimination method is actually not bad, especially when you have just a 2x2 system. And the system is not too hard to do, but it does require you to solve the system and then use most likely do some kind of undetermined coefficient method to solve the non-homogeneous equation. Well, actually, it would be homogeneous, so it shouldn't be that bad if you do elimination method. But of course, with a larger system, it will be probably harder to do. Nice thing about eigenvalue, eigenvector, and matrix exponential is that they both can work with higher dimension. You probably would use some kind of calculating device to help you figure out the eigenvalue, eigenvector, and do matrix multiplication. Elimination method, you really can't do anything like that. You're going to have to go through the process algebraically. So it does have the advantage of that using eigenvalue, eigenvector. You can use calculating device to help you out. Now that I have the homogeneous solution, then what do we do next is the following, is to now try to find a particular solution to the non-homogeneous system. How do you find the particular solution? Well, there are quite a few things. Find a particular solution to a non-homogeneous system. Either as a byproduct. So if you use the elimination method, you really don't have to worry about it because the elimination method will find the particular solution along with the homogeneous solution. So either as a byproduct of the elimination method, which is nice, or by formulas 13.3.2, which is for constant matrix A, with e to the ta, or 13.3.3, which actually, let me see, did I title that 13.3.3? Actually, I don't remember. Okay, I actually did not title 13.3.3. I'm going to title that now. This is theorem 13.3.3. And then the one with the e to ta is 13.3.2. There you go. So I actually forgot to title that. All right. So make sure you fix that in your notes. Or 13.3.3, which is with using non-constant. Oops. Matrix A of t with fundamental matrix capital X. Oops. And then once you did both of these, then what you're going to do is simply write your solution. And it doesn't matter which order you write them, but just to basically add the homogeneous solution and the particular solution together, and that gives you the entire solution X. So what I want to do is go through another problem with you using theorem 13.3.3. 13.3.2 is the e to ta, which shouldn't be too bad, and you're more comfortable with e to ta since we had spent the entire section 13.2 to do that. So I'm going to try to use this formula again, which is the fundamental matrix formula, using a non-constant coefficient matrix, and see how it goes. I can tell you that right now, these type of problems are extremely difficult with a lot of things going on. and any little mistake can totally ruin your problem. So hopefully I don't make any mistake while I'm making this video, because that will be a little embarrassing. So the problem I'm doing is actually on page 645, number 12. Okay, so it would be typical to your test question will be very typical to just like this one, where I give you a non-constant matrix A, but also will give you the general solution to the homogeneous system. So that way you don't have to worry about finding that, and you can just simply use it to form the fundamental matrix and proceed with the problem. So here's the question. Basically asks you to solve this. Solve dx over dt and dy over dt equal to, so that's d vector x, t over t minus 1, negative 1 over t minus 1, 1, 0, times xy, plus 1 minus t and 1 minus t squared. And the problem gave you the following. And let's say, given that the homogeneous solutions are 1t and e to t. So both of these are the homogeneous solution, and it makes sense because you have a system of dimension 2. So therefore, your homogeneous solution should be spanned by 2 vectors, and which we now have. So let's try to proceed with the problem. Okay, so first of all, I already know the homogeneous solution already. Homogeneous will be C1 times 1t plus C2 times e to t. So that's our homogeneous solution. Now let's try to find our particular solution. So our particular solution would be equal to x of t integral of x inverse of t vector b of t and dt. And the homogeneous solution would be attached to the back or in the front, depending on how you want to do it. So in order to do this, we already know vector b. Vector b in this case is 1 minus t squared. I do need the matrix x. So our matrix x is our fundamental matrix. I can form the fundamental matrix by combining the homogeneous solution together. So there are basically 2 choices. I could use 1t e to t. Remember, we do use the homogeneous solution as columns. Or I can do e to t 1t. Either of those 2 would work. It really doesn't matter which one you use. So just really pick the one that you like. I am going to just, since it's given 1t e to t, I'm just going to use that. So therefore, I'm going to say is that vector x sub p would equal to 1 e to t e to t integral 1 e to t e to t inverse multiplied by 1 minus t squared dt. So look to me, I should find the inverse first. So I'm going to go ahead and just focus on this one right here. That's what I'm going to use as my fundamental matrix. So the inverse of that would equal to 1 over e to t minus t e to t multiplied by e to t negative e to t negative t 1. Ooh, that looked messy. Alright, let's see if I can do a little bit of work to get this look a little nicer. I do notice the following. If I factor out e to t from the bottom, I do have 1 minus t, which is a very encouraging sight, because notice that when I have to multiply this by vector b, which is 1 minus t is 1 minus t squared. And nice thing about it is that 1 minus t automatically will cancel the 1 minus t. And 1 minus t squared actually factor to 1 minus t 1 plus t, which also means I can also cancel the 1 minus t on the bottom. So that's actually pretty good. But let's try to see if I can rewrite this. So I'm going to write this as this. If I multiply this into e to t, I just get 1 over 1 minus t. If I multiply by negative e to t, I get negative 1 over 1 minus t. If I multiply that to negative t, I actually go write this one. I'm going to write negative t e to negative t over 1 minus t. Because I want to just keep the denominator 1 minus t so that I can, make it look nicer. And then the last will be e to negative t over 1 minus t. So that look pretty good. Okay, still complicated, but hopefully after I multiply, it will become easier. So I'm going to go and just write out matrix X. That doesn't change. Integral of 1 over 1 minus t, negative 1 over 1 minus t. Negative t e to negative t over 1 minus t. E to negative t over 1 minus t. Multiplied by 1 minus t squared dt. So let's see what happens when I multiply this thing together. Okay, and of course I didn't do integration, so I'm going to keep the integral, but I'm going to multiply this out. So let's see, if I do 1 over 1 minus t times 1 minus t, I get 1. Negative 1 over 1 minus t times 1 minus t squared. Now, here's the important part. I'm going to look at 1 minus t squared as 1 minus t times 1 plus t. So then when I multiply that, the 1 minus t would cancel out, therefore becomes subtract 1 plus t inside the parenthesis. That's actually pretty simple. That's pretty good. I like it. The bottom, when I multiply, the first term becomes t, negative t e to negative t. And the second term actually come out to be the same, but it's plus e to negative t times 1 plus t dt. So that's actually pretty nice because I have 1 minus 1 plus t become 1 minus 1 minus t. So that just becomes negative t. So that's actually pretty simple. On the bottom, notice that the negative t e to negative t would cancel out with the t part when they get distributed by e to negative t, and therefore just leave me with e to negative t on the bottom. So after all this math, it's actually come out to be pretty simple. So now I can actually integrate this, so that's actually pretty nice. So when I integrate this, I get negative 1/2 t squared. And on the bottom, I get negative e to negative t. So if I actually multiply this out, I get negative 1/2 t squared. And then e to t times negative e to negative t becomes just minus 1. And to the bottom, t times negative 1/2 t squared become negative 1/2 t to the third. And then minus 1 also. So that seemed to be my particular solution. So that's actually not too bad. And so now I think I can write out my answer. Vector x is equal to, let's see, c1 times 1t plus c2 times e to t plus negative 1 over 2t squared minus 1, negative 1 squared t to the third minus 1. If you want to, you can combine them all together. It would be c1 plus c2 e to t minus 1/2 t squared minus 1. And then c1t plus c2 e to t minus 1/2 t to the third minus 1. Now, if there's some kind of initial condition, we can actually solve for c1 and c2. You know what? Maybe we'll give it a try. Maybe we do the problem actually number 12 did not give an initial condition, so I'm just going to randomly make some stuff up and hopefully it doesn't turn into something too big of a problem. So how about we are given that vector x of 0 equal to negative 2, 3. Okay, and then solve this initial value problem. Okay, so should be pretty simple. So therefore imply that negative 2 equal to c1 plus c2 times 1 because e to the 0, I'm going to just write it, e to the 0 minus 1 half 0 to the square minus 1. So that just tells me negative 2 equal to c1 plus c2 minus 1. So that means negative 1 equal to c1 plus c2. That's pretty good. Second equation, when I plug in 0, I get 3. So 3 equal to c1 times 0 plus c2 e to 0 minus 1 half 0 to the third minus 1. So this is even nicer because c1 actually get rid of. So therefore it's just c3, 3 equal to c2 times 1 minus 1. So c2 must be 4. And therefore imply that c1 must be negative 5. And so that's my constants. So now I can actually write out my answers. Vector x must equal to negative 5 plus 4 e to the t minus 1 half t squared minus 1. And negative 5t plus 4 e to the t minus 1 half t to the third minus 1. And if you plug in 0, you can see that it will be 4 minus 1, which is 3. And then when you plug in 0, it will be negative 5 plus 4 minus 1, which is negative 2. So that's pretty good. All right, so that actually is the last example I want to show you in 13.3. And that actually concludes 13.3, as well as actually the entire chapter 13. So beyond that, that's it. And I'm probably just going to give you class time to keep up the videos and try some of these problems. As you can see, some of these questions are not easy to do, and you really should try to follow along, or at least do this problem by yourself. And when you get stuck, you come back and look at the video and try to figure out what's wrong, and hopefully be able to finish the problem by yourself, and then you can try some of the homework questions, and hopefully you'll be able to do that on the test. This sort of question is not going to be easy if you don't practice. Okay, it's not that easy to complete them, even if you know everything. Put it this way, when I'm doing it, you know, I also nervous that I will make mistakes somewhere. Okay, but fortunately I make less mistake than you guys, so usually I don't run into major problem. But so far so good, I guess. It's always a possibility that I'm going to do a problem with you on the video, and then I'm screw up and I have to redo the video, or I'm going to leave it in there and just have to fix it. All right, so that's it, and I'll talk to you in the next video. Okay, bye bye.